Good morning, colleagues. Welcome to the second day of the DestinE user exchange. I do hope you enjoyed the inspiring and interesting discussions and presentations yesterday, and also the very nice reception here in the pleasant courtyard. Today's day is a full day, continuing on. The morning will be all about artificial intelligence. We'll have two sessions. The first one is already getting prepared here on AI, Earth System Model, and interactivity in Destination Earth. This afternoon we'll have a two-track program that will take place both in this room and upstairs in the Maritime room. I'd also like to take this opportunity to remind you that the posters will still be up throughout the day, both outside in the courtyard where you found them yesterday, and also the demo stations. If you turn out here and then to the left on both sides, where you'll be able to interact with some of the interfaces and have people who are implementing these activities explain the services, the pilot services, the demonstrators, where you really can get hands-on experience with what Destination Earth applications and demonstrators do in action. Without further ado, I'd like to now hand over to Sarah Hana to introduce the first session.
Yeah, good morning, everyone. We want to talk about AI now for the next hour and 15 minutes. At first, we're going to have a look at an AI Earth system model. I myself will give an overview, and then we have invited Fernando, who's going to have a look at AI climate models. And then we are also going to talk, as already said, about interactivity. And we are going to have a look at the platform. And we have invited Arturo and we have invited Florence to talk about conversational AI and trust and ethical use of an AI in our DestinE platform. So I think we get a great overview. We're going to talk about modeling. We're going to talk about interactivity. And I want to set the stage by giving you an overview of how realistic and how good these AI models actually work for our Earth system. And within DestinE, we're going to have a specific focus on AI Earth system component modeling. I want to give you an overview about our AI weather forecasting models at eCMWF. Because I want to convince you that these AI models are worth and they can make realistic and very good weather forecasts. And we at eCMWF are convinced by that, which is why by now we have two operational machine learning weather forecasting models. We have one deterministic Earth system, we have one deterministic weather forecasting model and one ensemble weather forecasting model. And these actually run along our traditional physics-based models. So we really take this time at the moment to evaluate both models and run them in parallel. So what are these two models? We have a deterministic forecast where we start from one initial condition and produce one forecast. We call this model the AIFS single. But then there's uncertainty in the system. Our initial conditions are already uncertain because we cannot observe everything. It's already an estimate of the actual state of the Earth system. And also the forecast itself is uncertain. So we capture uncertainty both in the initial condition and in the model and produce our ensemble forecast. This is something that we do with our physics-based models as well, and we have implemented it in our AIFS ensemble CRPS model that is running operational as well. And something that I find very important to point out, because I myself am a machine learning scientist at eCMWF and I look at scores all the day. But when we ask our users what is actually one of the benefits of these AI models, they many times say that they're just so quick because our AI forecasts are actually ready in minutes, whether our physics-based weather forecasting models need hours for forecasting the weather. So I think it's really important to point this out because it will become important as well when we talk about interactivity. Because of course these models being able to make quicker forecasts also make us able to interact with these forecasts in a very different way. But then we talked about speed. Let's talk about the quality of these data-driven forecasts. And in general, we can see that these data-driven weather forecasting models show improved skill in comparison to our physics-based baselines. The forecasts for most variables improve by about 1 day in lead time. What does that mean for us users when we look at our weather forecast? If there's an event, the data-driven weather forecasting model might actually forecast it about a day earlier than our baseline. And you see our two key scores for both our models. So for the AFS single, you can see errors of tropical cyclone tracks forecast, and the red line is the AIFS, the blue line is the IFS, our physics-based weather forecasting model. And you can see how the red line lies below the blue line and therefore shows this improvement in forecast quality. Similar image for our AFS ensemble forecast. Here we can see the CRPS score of surface temperature of our AFS weather forecasting model and the IFS. And you can see again how the forecasts are improved with respect to CRPS score. And now the question is, why do we think, what's the magic behind this? What makes these good forecasts and the development of these models possible? And I think I would like to focus on 3 things here. At first, I want to mention Anemoy. So Anemoy is an open source software ecosystem that is developed by ECMWF together with the member states. If you want to hear more about this, Harrison is actually going to talk about it in about an hour, about 15 minutes only about Anemoy. Why that? Because we are quite proud of this. I think it shows very nicely how European collaboration makes these models possible, and the development of these models in such short time. The models that we have developed within Destination Earth, our AI Earth system component models, we were able to develop them so quickly because we can build off software that is made available within Anemoy. And it's not just our operational weather forecasting models that run in Anemoy, we also have regional models. For example, PRIS from Met Norway that is implemented in Anemoy, and DWD is implementing AICON, the operational weather forecasting model within Anemoy as well. So this open source ecosystem covers our entire pipeline, from building data sets to defining the model, training the model, and then running inference. But then, of course, the software is not enough. I have said these AI forecasts are super quick, that's true, but we do need resources for training, and I think this is another very important pillar in the development of these models, that we have access to compute, for example, via EuroHPC and the AI factories that give us access to this GPU compute power to develop these models. And then, of course, we need the data. Machine learning models need to be trained on very skillful data, and in the weather or in the Earth system domain, we're very lucky that we have that data. We have collected data for many, many years. We use big data sets like ERA5. I'm going to use ERA6, the digital twin data from DestinE to train these models with first-class, very good quality Earth system data that we can train on. And all these things we use to build our AI models. And now I want to talk about the AI Earth system component models that we are building and we have been developing within DestinE. You've seen the operational AIFS models. Initially, they actually focused mostly on the atmosphere. And within DestinE, we want to bring these efforts to model the entire Earth system. What does that mean? Not only the atmosphere, but we also want to model sea ice, ocean, the land component, the ocean waves, and hydrology. And we have chosen an approach within DestinE where we build component-wise models that are forced by the atmosphere. So we feed information from the atmosphere to these component models. And I want to give you an overview over key results that we were able to produce for the different components. And then I invite you to approach us or scan the QR codes if you want to hear more about these component models. So what all these models have in common, it's a component AI data-driven model that is forced by the atmosphere. And then some of the results that we are interested in is how do these AI component models react to this forcing from the atmosphere that might be extreme, that might be out of our training distribution. And here I show you a simulation of the AI emulator AI land for the land component. And this AI land model is forced by error 5. So forced by, let's consider it the truth of the atmosphere, the true state of the atmosphere. And what we can see here is a simulation of soil moisture of summer 2022, which has been one of the driest summer in Europe. And therefore, this is an event that lies outside of our training distribution. And you can see, it's now starting over the simulation, over the summer, the soil dries out, goes from green to brown, and this is a very good result because we are able to react to that forcing from the atmosphere reasonable, in a physical, reliable way, that even though this event lies outside, is an extreme, lies outside of our training distribution. For the ocean component, we are modeling the ocean and sea ice together. And here I show you a simulation of sea surface temperature in the purple and yellowish colors and sea ice concentration. This is actually a simulation that's running for an entire year. Again, we provide forcing from error 5, so forcing from the atmosphere. And something that I want to point out is the sea ice. You can see how the sea ice grows in winters on the respective hemispheres and then reduces again in summer. And the red line that you can spot, yes, it is very nicely visible, is the observed sea ice edge. And you can see how the simulated sea ice edge matches this red line very nicely. So again, we see a very physical, reasonable, physical, consistent reaction to this forcing from the atmosphere in these simulations. Let's stay on the ocean and look at the wave component. I show you a simulation of significant wave height forecasts here, because we have went a step further and actually provide AIFS forecasts to our AI wave model. That means we have on the left our data-driven wave forecast using the DestinE AI emulator of the wave component, and on the right our operational wave forecast. I'm going to replay this. You can see there was a storm in the North Pacific that created large period wave swell that is traveling over the entire Pacific Ocean. This was again an out of training distribution event. It created a surf event on Hawaii that's only happening every 10, 20 years. But at the same time, it also caused damage along the Pacific coasts. And I myself actually work on the wave component. And it was very impactful for me to see this. Because when you see, well, this data-driven model that I'm developing is actually able to forecast these extreme events that cause damage along the Pacific coast, this was very impactful for me. You see how these two forecasts align. Our data-driven forecast, you do notice a slight difference in the forecast, but in general, the structure of the forecasts are very similar. And last but not least, I want to talk about the hydrology component, where we model river discharge. And you can already see this looks quite different. This is not on a globe anymore, yes, because the observations are point-wise. So we are handling very long time series and actually go for a different model architecture there. And you can see in blue the simulated river discharge simulation, the simulated river discharge, and in the black dashed line, the observed river discharge. And you can see how these lines match. At first, we capture the seasonal variability, we capture the peaks of river discharge, and we also capture the amplitude relatively well. Now, in the next years within DestinE, we want to combine these component models into an AI Earth system model. We have these component-wise models that are all receiving information from the atmosphere, and now the next step is to bring these models together, to let them communicate, to make this into a coupled Earth system model. And we are also going a step further. All these AI Earth system models that I have talked about earlier, these are global models. And coming next, we also extending the regional AI modeling capabilities. We know regional modeling that's data-driven works well. We've seen this within Anemoy. We've seen this in our member states. So the next step is to bring this into DestinE and make it configurable. So we've talked about this yesterday, that there's a lag for location-independent models, and this is exactly what we are targeting here. We want to build a regional model that is not just working for one region, but is actually configurable. And then the resolution can be selected, targeted where it matters and where the user is interested in these forecasts. So I'm very excited for this project that is coming next. And this brings me to my closing slide. The key messages that I want you to take away from this talk is that, yes, AI models enable faster and very cost-efficient simulations of our Earth system. We see that the predictions from these data-driven models are improved in comparison to our physics-based baselines. And we want to use this to enhance the interactivity. We have two talks that are going to talk about this enhanced interactivity. And there's also going to be a talk about methods like forecast in a box that are enabled because these AI models can run so quickly in the next session. And with that, I want to finish this talk. I want to invite you to ask your questions via Slido. Maybe our colleagues over there can share the QR code. Please put your questions into the Slido. And in the panel discussion, we are going to only take questions from Slido, so no questions from the audience. Just put them in the Slido, please, and we will answer them after the last talk. Thank you very much. I hand over to Fernando.
Hi, everyone. So today we'd like to share with you the work we are doing to build DestinE's climate emulator for being a fast, stable, and scenario-aware system. So this work is a large effort between ourselves, Predictia, with CSIC, BSC, and FCJ. And it's under a contract managed by ECMWF, which actually they provide very important technical support on this development. So in a nutshell, what we are building is a deterministic AI-based climate system or emulator. And the key difference with the previous presentation that Sarah shared with us is that what we do is a seamless integration of the different components. So with a single emulator, we will include the fields from the atmosphere, the land, and the ocean. So our task here is to take advantage of existing AI weather models and adapt from an AI weather system to be a climate emulator. So for that, we are based on the Anemoy framework, and we have three key goals and challenges that we would like to share with you today. First, maybe the most challenge that we had so far was achieved a stable long-term climate emulations. We need to be able to make projections of hundreds of years, and that was a key goal that we had to address. Then we need to capture, of course, climate change signals and patterns. We need to replicate physical and climate properties of the physical models that we are replicating. These models are, as you know, climate DT simulations, and we are currently working on enabling the emulator for being a scenario aware, so we can do future projections under different future scenarios. So far, we've been working on experimental prototypes, so we have not been working with climate DT simulations because there is a good breadth of air system simulations out there. So for this prototype, we've been working with CIMIC 6 archive. Particularly, there are two air system models that we use. Using two Earth system model, we can make the exercise of the results that we have are not model dependent. So we've been using CSM2 and UKESM for 3 different experiments. Pi control, why pi control? Because there is no climate change signal, that's just interannual variability, which actually is a good control system to allows us to build a stable emulator. And then we work with historical and SSP future scenarios in which we can let the emulator learn the anthropogenic climate change signals. We usually use over 100 years for training. Currently we use relatively coarse resolution, 1 degree in the horizontal space and on daily means. The outputs that we include is just a subset of the full outputs that the final emulator will include from the climate DT simulations, but it's a good breadth of the full output that we will include, including the 3D atmosphere, 2D fields, including relative fluxes, important. We are learning sea surface temperature and different forcings, not only greenhouse gases, but also we include the day of the year, the latitude, and so on. Before we get to the goals and the results that we have so far, we make use of Aqua tool to evaluate and validate our emulator. This makes much sense for us because Aqua has been developed explicitly for evaluating climate DT, so there are a number of diagnostics that we can take advantage of. It's also in active development, so any new feature or diagnostic, we can actually use it. And the new diagnostics that we are implementing for the climate emulator can be brought back to the main tool so the community can benefit from our developments. So the first goal, achieving long-term climate emulation. For this, we worked intensively, and we found, we proposed a solution. I'm not going to go into details, but there is now a different paradigm of how the autoregressive system advances in time. So now the emulator is able to choose what to remember and what to inference in the next step. So now you see on the left, on the top is global mean surface temperature, on the bottom is global mean sea surface temperature. You see how the emulator in blue nicely captured the seasonal cycle throughout of the 30 years without any evident climate drift. Same for sea surface temperature. But for sea surface temperature, it's evident that the emulator is not capturing either interannual variability and multi-decadal variability. And this is still a limitation that we have, and this it's a work in progress. But what you can see in the video is how the emulator nicely captures the small scale pattern. So you see the weather system, you see the contrast between polar regions, mid-latitudes, and so on. So the emulator does not show any sign of stability or artifacts. Second goal was enabling the emulator to capture and learn global mean trends. So for this, we've been working only including CO2 so far, and this is results for the historical period. Again, it's the same plots. On the top is for global mean surface temperature, on the bottom is for sea surface temperature. You see how the emulator, albeit some biases, nicely capture the global mean trends for both, but again, you see how the emulator currently lacks a good representation of interannual variability, which we know it's important. Niño-Souther oscillation at a yearly scale actually determines our climate. So this is still work in progress, but the emulator nicely captured the global mean trends. Third, we need to be sure that the emulator capture different climate and physical properties of the Earth system models. For this, we have a good breadth of diagnostics. I'm going to show just a few. You see how the emulator nicely captured the climatology, the contrast between polar regions with mid-latitudes, the orography, the contrast between the sea and the land. So it's nicely captured the climatology. Then on the bottom, you see cross-section. It's from pole to pole and from the surface to the upper stratosphere, and you see how the emulator nicely captures the structure of the temperature. So warm temperatures on the equator, and then it gets colder towards the pole and towards the stratosphere, nicely capture the cold point of the stratopause. There are some biases still that you see on the right, particularly the polar vortex in the southern pole, but this is mainly because the emulator is missing some inputs. For example, we are not giving the emulator stratospheric ozone. If you are not having stratospheric ozone, you cannot develop the ozone hole, you cannot develop the depth of the polar vortex, then you've got the bias. So it's good it's there. For the final emulator, we'll include ozone, and this bias probably will go away. Then we also check that the emulator, not only visually, but more in a diagnostic way, it actually captures the features at different scales, from large scales to small scales. And we also make sure that the emulator nicely captures different modes of variability and teleconnections below a year time scale. So here we just show how the emulator nicely captures the dipole fingerprint of the North Atlantic Oscillation, with the lows over Greenland and the highs over the Azores Island. And finally, and this is work in progress, these are first results that we have. It's how we train the emulator to be scenario aware. So the emulator is the dashed or dotted line, and the Earth system model is the thick line. The emulator has only been trained with the historical period in black and the high-end emission scenario in red. And you see that for both surface temperature on top and sea surface temperature on the bottom, the emulator does a good job capturing the historical period, the high emission scenario, and then it's able to generalize to a good extent to the medium scenarios. But when you get to the low-end emission scenario, it gets colder. It's too sensitive to changes to CO2. So it's not capturing the climate inertia of the system. It's a work in progress. It's about finding solutions. Actually, we've trained a new emulator that now nicely captures the climate inertia of the system, but it's work in progress, so these are exciting results. So just to finish with the goals that I put forward before, we've got a climate emulator that now it's a long-term stable, replicates different key physical and climate properties of the Earth system models, nicely capture the long-term warming trends, and work in progress with enabling the scenario-aware capabilities. And finally, from now till the end of the year, we'll work on bringing this expertise, working with CIMIC-6 model, to build the emulator using climate-DT simulations at 25-kilometer scale. Thank you.
Thank you very much, Fernando. So we move now on to the future of DEA, conversational interface for Earth intelligence with Arturo Monieri from Alia Space.
So good morning, everyone. I'm Arturo Monieri from Alia Space, and today I'm going to talk about the future of DEA, introducing the conversational interface for Earth intelligence. Let's start with the services. On the DestinE platform, we have a bunch of different services, from data access to data visualization. We have urban, climate, and so on. On the other side, we have the users of the platform. Shown here in the public dashboard of the DestinE platform, we can see different users grouped by categories. So we have users coming from public sector, from private sector, from media, and so on. So these are our users. And the first question here is, how can a user today create something like that? So get results from service one process these results using service 2, and finally, just for example, publish these results online. And yeah, the answer is yeah, this is perfectly possible today, because for every service we have graphical user interface and we have also the application programming interface. But the APIs and the GUIs limit how many users can benefit from software. So the question here is, how many of our users can work with an API or, let's say, write some code? Around 30%. And how many users can use a graphical user interface? Around 60%, for sure. Many users. But how many can use a natural language? All users. So can we use natural language to access the services all from one place? Can our user make requests like, let's say, show me a temperature anomaly stripe for Madrid from 1950 to 2020, or show population density map at a NUTS level 0, or show RGB ratio over Brussels last week? So I'm very excited to introduce today the conversational layer for Earth Intelligence in DEA, where natural language becomes the new interface. Conversational interface, in this case, for tools, for Earth data, and for insights. But now I want to show you some more practical example of our assistant, of our agent inside the DEA. So this is our assistant in the DEA service. So first of all, I can ask something like, hey, how can you help me? So the agent reason, and in this case we respond showing its tools, its capabilities, from climate data to Earth observation and satellite imagery. So in this case, for example, hey, show me DestinE layers, second generation using mini DEA. What's happening here? In this case, we have inside conversation, directly into conversation, we have a preview of data, not just a wall of text or just numbers, but we have real data coming from operational services hosted on the DestinE platform. So the widget is interactive, so I can change a layer, can change data, and so on. And in this case, if I'm happy with the results, I can add this context to the slide, so it can be part of my composition or my story. In this case, we have just another example. Hey, add layer in a dedicated slide for each one of these this layer and some description. As you can see, we are using just natural language, and we are using the real data from the services. It's not data inside the knowledge base, but data coming directly from operational services hosted on the platform. So we can move just with another example. We can not only just visualize data, but we can also interact with data. We can just add some different services. In this case, we are, hey, give me the temperature anomaly stripe for Madrid from 1940 to 2020. In this case, we are calling another services hosted on the platform, which is Earth Data Hub, which is an operational services on DestinE platform. We get data, we retrieve data, the real data from the services. We can plot the results inside conversation. And if I'm happy with the results, with this preview, again, I can add these data sets in my story, user story, in my content. In this case, we are adding the plot. In this case, in the slide content. As you can see, I'm just using in this demonstration natural language to access services and get data. In this case, please show daily cooling days, and again, different kind of plot directly inside from conversation. I can change interactively the parameters, and if I'm happy with the results, I can add to my final story to compose the final results. The agent is capable to call different tools, so plans different steps to achieve the results. In this case, we have, just for example, we have put the plot as a slide background in my stories, just to show a different use case. In this case, we are now just another example of processing interface. In this case, hey, show NDVI over Brussels, July, blah, blah, blah. And in this case, we are calling external services, in this case, Copernicus Data Space Ecosystem. So our connector now talk directly with Copernicus Data Space Ecosystem, gets data, call the interface, the processing API, and get the results that I can show directly inside my conversation, and we can zoom in, zoom out, just to have a fast preview of the data, of the assets. And in this case, we can also show the payload that I sent to the agent sent to the Copernicus Data Space Ecosystem. And if I'm happy with the results, I can add this as asset into my story, as a georeferenced file directly into my composition in my user story. So also in this case, just using natural language, I'm using an operational service, real-world data in my conversation. So different services, different use. In this case, we have Sentinel-3, ALSI, over Venezia in a specific time. Also in this case, we are calling different tools using our connectors, just using natural language, and we access different data sets hosted on the Copernicus Data Space Ecosystem, and we can show the final results. The process is executed on the fly, so no pre-processed data here, but just calling the real and operational interface in the CDSC. And also in this case, I can add my results coming from the agent directly into my story. The agent, if you want, you can also explore the reasoning steps that the agent calls and the plan that the agent executes. Also in this case, we have the assets directly into DEA, directly in the user story. Just another example showing population density in Germany, Italy, and space. In this case, we are calling different services, in this case Eurostat. As you can see, also here we have the widget inside conversation. We can change some parameters in the plot. As here we have the real data. We have in the conversation a link just to reference, just to refer to real data coming from the external APIs directly into conversation. So just to verify the data. And just another example, just kind of visualization. We have a choropleth map in this case at a different NUTS level. you can change some parameters. If I'm happy with the results, I can add also these assets directly into my story. So I can ask to our agent, hey, add to the slide. In this case, the agent reasoning about the steps, which tools, call, and finally, the asset is directly inside the story. So we are creating a user story just using natural language with external and operational services. So this is just an example of final story. In slide 1, slide 2, we have different data sets on board, different kind of plots from operational services in DestinE platform, from Copernicus data space ecosystem, from Eurostat, and so on. Also, you can interact with the story. You can browse, you can change perspective, and so on. You can explore interactive with the story using just a browser. And that's all from our side. And please join us for live demonstration at demonstration area, starting from, I think, from 10:15. Thank you very much.
Thank you. Thank you very much, Arturo. So we move on with Florent Luisotto from eXchange, and we will see a bit about trust, ethics, and quality for AI on DestinE platform.
Thank you. Hello, everyone. So I'm the operational director of eXchange, and I'm presenting today on the following topic: trust, ethics, and quality for AI on the DestinE platform, and so on, e-learning by eXchange, that is a resource to build data and AI projects with an ethical approach. First of all, I have to say that we are not a technical service, but like I said, a resource on DestinE Learning and Training Hub. And our interactivity with DestinE is regarding users and providers of the platform. But let's begin with a small explanation of what we mean by ethic. So what is ethical data use for DestinE users? The aim of data ethics is to foster trust between data holders, data users, and society. The ethical use of data ensures that data-driven innovation does not conflict with our European values, and ethics is therefore a lever to build trust among stakeholders and to facilitate responsible data exchange. But first of all, to understand our role on DestinE and our link with direct users and providers of services on DestinE, I have to explain what eXchange is. So eXchange is a French association with members from public, private, and academic sectors, like the French Space Agency, the National Institute of Geographic and Forest Information, and so on. And one of our major partners is the French Ministry of Ecological Transition. So our work is to build a framework of trust for the ethical development of the data economy. So it's based, how we do that, it's based on the ethical charter for data and AI, which I will come back to. And we focus on data because with that data, we believe that AI cannot be performant and efficient. So we have a mission to sensibilize decision makers. We have 4 main areas of expertise: ethics, that is points today, but also legal matters, economic models that incentivize data sharing, and technological solutions that ensure confidentiality. So working on this topic serve our main mission, that is to help accelerate the success of data and AI collaborative projects in the public interest as digital twins or data spaces. So we enhance the positive impact of data and AI projects, and it has to be a competitive advantage that we believe. We do this by raising stakeholders' awareness of ethical issues related to the use of data and AI, and by removing barriers to data sharing. But how can we do this? As I said before, we built a trust framework thanks to the ethical charter. So, excuse me for this all information about ethical charter, but I have to it's like a little quick masterclass of ethical principle. So this charter is a framework built on European rules and organized around 6 ethical teams. It was co-constructed with scientific and legal experts, citizens, and reviewed regularly. The first ethical theme is about the positive impact on society at the respect of the Sustainable Development Goals. For example, be aware about the level of the benefits regarding the environment costs, regarding AI and the use of AI. It's important to have this principle in mind. The second one underlines that it's essential to include citizens and end users along the project. The third one is about covering security and privacy topics. For example, in a digital twin, personal data can be used, but it's important to protect their privacy. End user rights mean that the project must be transparent and provide clear, accessible information as well as free choice. The end users have to be informed about the fact that AI is used, for example. The fifth ethical theme is about data processing performance regarding robustness, explainability of the algorithms. And the last theme of the ethical charter concerns reciprocity between partners. This means we must raise awareness through collective learning and reciprocity. So these principles are a response to challenges regarding use of data in AI, such as Earth observation data and climate simulations. So the use of those data can support better decision making, but they also raise some of these ethical challenges. We focus here on 4 major challenges. For example, the high environmental impact, increasing energy consumption, carbon emissions, and the use of natural resources. New harms and societal risks can be identified too. The use of climate data and AI may reinforce existing inequality. For example, climate data could be used by companies to identify and exploit new resources in previously inaccessible regions, potentially to the detriment of local communities and ecosystems. A third challenge identified is unreliable results and poor decisions. Insufficient data quality biases on AI systems can produce inaccurate outputs and lead to misguided decisions. And to finish that, another major ethical challenge is the loss of sovereignty and unfair value capture, dependence on non-European infrastructures may reduce strategic autonomy. Saying that, all that, it remains difficult to integrate ethics while building data and AI projects. So how does e-learning that I spoke in the introduction support ethical data use? So with e-learning platform that you can find on the training hub of DestinE, we aim to train users of the DestinE platform to understand these ethical issues. we offer a tool that combines three key features. Some e-learning modules. This enables stakeholders or project manager to become aware of the ethical issues surrounding data and AI use. There are 20 e-learning modules that are each one regarding a principle. I spoke about six thematics, but there are 20 ethical principles that you can train on. There's available too an ethical scan, which identifies the ethical risks of the project, beginning the project, just to at the beginning of the project, just to question if the project has some issues and ethical issues. And to complete the journey on this platform that is on DestinE, there's a maturity diagnosis that implements an ethical approach for the projects. So, in conclusion, we believe that in order to ensure the ethical and trustworthy use of data and AI, and in the context of AI, it's really important to be able to offer, as we do, tools that enable global ethical approach to be implemented in a practical way within every project, and this is available on DestinE platform for all the users and all the providers of the services of DestinE. So thank you for attention, and if you want a demo session, we are on the demo session there at 3:30 this afternoon. Thank you.
Thank you very much, Florent. So now we start with question and answers. So we start first from Slido, and probably we have question from Slido. Yes, we have questions from Slido. So first question is, how do the AI ESM component and the climate emulator complement each other? And probably that is for you, Sarah.
Yes, I can take that question. So in general, the models are separate, so it's two separate models. But we do have regular exchange with the colleagues from Predictia. We do build on the same software framework, so everything that we bring into Anemoy, the other models can use as well. And we actually have a nice example for that, the residual connection that is used in the AI climate emulator within DestinE. We're also using that or trying it out for our AI Earth system component models. So I would say that's a nice example for complementation between the models.
Thank you very much, Sarah. So second question still from Slido. Can a climate emulator accelerate the production of climate digital twin simulations? And I think that is for you.
I think what the climate emulator may bring is complementing climate simulations in a way that the climate emulator is faster, and in due time we may be able to project different future forcing scenarios without necessarily having to run the full climate DT set of simulations. So I think in that way the climate DT, the climate emulator can complement climate DT simulations rather than accelerating the production.
Thank you, Fernando. So third question from the audience. So which LLM is they are using for the chatbot?
Currently we have tested different models. In the demo shown before, we used the Qwen open source model, but we have tested also the GPT-OSS models and Eve from ESA. So from our point of view, it's just a kind of configuration inside our agent. So we can choose the model that we want.
Okay, thank you very much, Arturo. So another question from you, Arturo, and then we move to other questions. So how do you validate information given by the AI assistant?
We have put in place an evaluation framework, observability evaluation framework, in terms of the trace that go from agent and external systems, but the data, in principle, are trusted data because we have configured real-world system from ESA, from DestinE, and so on. So the data is coming directly from these trust sources. But we have on board also an evaluation framework in terms of tracing and so on.
And this brings to me a question that I have a bit for all the panelists. So we have seen the value added out of a better Earth AI modeling. We have seen also climate simulations. We have seen better easier access and trust. But I would also like to understand a bit more about the limit, a bit the risk and the operational readiness. And on that side, I would start probably with Sarah. So when we combine several AI system components besides the models, what is the main scientific risk to controls first? So physical consistency, data quality, scale differences, or validation across components.
Sorry, I'm coordinating the questions at the moment.
Sorry.
What was the question?
So the question was about a bit the limit, risk, and operational readiness for, let's say, the different elements that we have seen. So when you are combining all the different components inside your model, so what is the first main scientific risk that you want to control first? So physical consistency, data quality, scale differences, or?
Yes. So I think physical consistency and data quality come together because we have seen with most of our models that physical consistency can be learned from data. So I would say data quality is very important, data availability, data consistency between these components. This is actually a challenge that we see if we have data that is not consistent between two different components that can impact our model performance.
Okay. Thank you very much. And for you, Fernando, still from my side, so when we have these climate simulators and emulators outputs, so how should users understand the limits of these emulators before using them for adaptation or planning decisions?
So the climate emulator will be based on climate DT simulations. So it can get as good as climate DT, cannot get better. So first, we need to have a good evaluation and validation of these simulations, understand the limitations of them. And on the same side, then we need to understand and evaluate comprehensively how the emulator is able to replicate the climate DT and to what extent.
Okay, thank you. And Florent, so when we talk about all these AI-enabled Earth system services, so we have bias, we have set a reliable result, we have, you said also loss of sovereignty, environmental cost, but what is the most one urgent risk that we have to address? Because otherwise we risk to lose our, let's say, way. So what is the most important risk that you say would be the first one to address? Out of, you said a reliable result, poor decision, loss of sovereignty, environmental cost. So what do you think that we should tackle first?
So which risk is most urgent to manage first? That's the question, yeah? I don't have a good answer for you because there's no order. I think that all these risks have to be considered. But like I said before, the problem is how to consider them. And that's why the fact that we have developed on DestinE some tools to support users and providers to be able to put a really ethical approach, global approach in their project. It's, I think, a key to be able to notice risks.
Okay, thank you very much. So, question from the audience about how does the atmospheric model deal with the aerosols and atmospheric chemistry? So, that is more for fun.
So regarding the climate emulator, currently we have implemented CO2. Then we are working on including different long-lived greenhouse gases, methane, N2O, CFC. And then from there, when we have the key climate signal, then we go to aerosols. We would start with volcanic eruptions. You saw on the global mean figure that dip in the historical period was not captured by the emulator because we don't have, for example, volcanic eruptions, aerosols. So we don't get, for example, Pinatubo's eruption deep in the historical period. So that would be next, and then different forcing aerosols to capture regional signal. And regarding chemistry, for now it's not envisioned to include chemistry so far.
Okay, so it's a very specific question. And so is the AI wave model preserves the spectral nature of EC1, or does it predict integrated parameters only? So that is very specific.
Yeah, that's a very specific question. I can try to give it some context. So EC1 has a spectral representation of waves at every grid point in frequency and direction. And it's a very high dimensional. We don't actually do this in our AI models. We use the integrated parameters only. I'm very happy to talk more on a coffee break if the question actually comes from a person from the audience. Very interestingly, what we do see is that we are able, though, to capture the spectral nature of the wave swell propagation by only looking at the integrated parameters. We have looked at some very interesting case studies there, and I'm happy to share some more details to the person who asked that question.
Thank you very much, Sarah. So we have another question about the climate emulator. So climate emulator runs will be tunable on a user level on one day. So really customized for the user location.
Good question. So far, it's not envisioned to be able to address that, but it's a fair point. No, so far it's not. We are not addressing the tunable on a user level.
Okay, thank you very much, Fernando. So I would like now to focus a bit of a question for the coming 2 years. So I would like you to predict a bit the future, and that is so. We have discussed about the value added. We have discussed about the limits. Now, I would really like to see or ask you your opinion about what will be the key for the next 2 years for advancing AI-based search system models and AI-enabled services within DestinE. Compute, data, model performance, trust, usability, or something else. So clearly from your perspective for what is the service that you provide inside DestinE. So I will start with you, Fernando. So for the climate emulator and scenario exploration perspective, so what will be the key for the coming 2 years?
So far, the climate emulator is deterministic, so we are not estimating and constraining the uncertainty, and that would be a key step forward for the climate emulator on the next phase. Be able to actually capture the internal variability of climate DT simulations so that we have a better understanding on the uncertainties in future projection. We can better understand and distinguish internal variability from anthropogenic climate change signals, for example.
Okay, thank you very much. So, Arturo, from your perspective of interactivity and conversational interface perspective, so what will be the key success factor elements for the coming 2 years?
I think that in terms of AI, we are just at the beginning phase, but I really think that the conversational interface will be the future for software in order to allow easy access to and the use of data because it lowered the barriers with machines. So I think that it's the first one interface, the natural language, human interface. So I think that we are at the beginning phases, but I think in future the conversational interface with the software in general will be the future, will be the normal.
Okay, thank you very much. Florent, from your perspective, from trust, ethics and quality?
The perspective, it would be regarding the use of data and AI. I think that maybe open the data, the sensitive data, strategic data from, and for example, from private sector organizations could be very interesting to increase the set of data and to have some possibilities really important and for AI systems. And but again, trust has to be built between stakeholders. So, for example, for digital twins, it could be really relevant and powerful to have some set of private sector data. So that could be an open strategy for the future.
Okay, thank you very much, Flora. So, Sarah, from your point of view of the whole Earth AI modeling.
Yes, it's a very good question. I think in the next years we want to make our models more powerful. We want to make them more flexible. We want to make them handle different time scales and the different components. We want to combine these components to each other. So I think we are looking forward to first making the models better. You asked what do we need for that. So yeah, we need the data. I think we have very good data quality already. We of course need the compute. This is key for developing these powerful AI models, for training them. And then I think the performance of these models comes with the availability of powerful compute and good data.
Okay, thank you very much. So now, if you would have to summarize in 1 minute about your presentation, so your side of the different aspects of the service that we have presented, so what would be the key message you would like the audience to bring away? And I start with Arturo on your side.
I think that we have to move from existing interface to simplify the climate and Earth observation data for everyone. So I think that we have to simplify something in the overall process, and conversational interface will be could be a good candidate for this kind of new approach, I think.
Thank you. Flora?
Like I said, I hope that DestinE providers and users will use the e-learning tools, because I think it's really important that they have to be aware about this use of data and AI. And for example, OpenAI, there's launched a competition with data, climate, and data observation Earth and AI. And the challenge is to find some archaeological sites in the Amazon, but they haven't involved the local communities and the owners of the territories. So it can be super interesting to find that archaeological sites, but it has to be in a good way, and I'm not sure that sometimes it's really for good. So that would be my conclusion.
Thank you, Roland.
For the climate emulator, I think the key message is that it may come to complement climate DT simulations, providing the users and policymakers greater speed and testing possibilities to address different potential policies, addressing different emissions pathways, not having to wait for the numerical models to run hundreds of years.
Yeah, I think the key message from my side is that these AI, there we go. The AI Earth system models are super powerful. It's not just a trend, they will stay around. I would that to be my key message. We have seen not in my presentation, but also in the other presentations, the AI tools can be super powerful. We want to bring them to the user, we want to make we want to make them trusted, and we will use them. They produce good forecasts, and that would be my key message.
Thank you very much, Sarah. So I see two questions from the audience that I still like to ask before closing, because I think they were quite interesting. So we've seen one question is about climate emulator. How can it accelerate the production of climate digital twin simulation? And the other one is about how the AI Earth system modeling component and the climate emulator complement each other. And I think that is quite key, interesting element. So how all these different elements working together and what is the benefit out of that? So speed, precision, so what you see as the key benefits of?
I think numerical models need quite some computational power, but I don't think that's the key delta, because we are getting more computational power. Also, long-term stable simulations is not a delta, because we've got climate DT simulations, which are we can provide that already. So I think the key part that the climate emulator is bringing up, which complement each other, is speed and testing possibilities, which actually complement climate DT simulations.
Okay, thank you very much. So if there are no other questions, I remember you that there will be demonstration during the day of the different services. You can speak with the different authors here and the speakers and ask all your questions. Thank you very much for your attention, and yes.